Hello everyone. Just want to do a quick recording on this concept of domain and range. I've had a few questions and it's much easier to do a recording than to try to type everything out. um, Domain and range. There's several different ways of looking at domain and range. I want to pick two for this recording. Algebraically and graphically. How do I recognize domain and range algebraically? And how do I recognize it graphically? Meaning in an equation and obviously in a graph. So question number 7 on the homework. What is the domain and range of the graph of y equals x squared minus 1? So they're giving us an equation. So they're giving it to us algebraically, but they want to know something about the graph, the domain and range of the graph. So I could look at it either way. So let's do it algebraically first, since that's what we see right here. Y equals x squared minus 1. So my first question is, what is this thing called domain? Domain is every single, or the set of every x value that will work in my equation. So what does work mean? So if I have, let me grab a marker here. If I have this y equals x squared minus 1, can I plug in, let's just say a negative number, negative 10? Is it mathematically okay? Meaning, if I plug in negative 10, can I work it out? Negative 10 squared, is that possible? Can I take a negative 10 and multiply it by itself? Sure. Can I put in a fraction into x value? So would it be okay if x was some fraction? Sure. Can I take 1/2, multiply it by 1/2? Sure, I can do that. There's nothing wrong with that. Can I, and we can just keep going through this can I questions. Excuse me. So like a negative 10, what if I went to negative 100 or a negative 2000 or negative anything? Is there any restriction on what kind of number that I can multiply by itself? Because that's what squared means. No. I can put a fraction, I can put in a positive number, I can put in a negative number, I can put in a decimal. There's no restriction on the type of number that I can square. Okay, so the domain of y equals x squared minus 1 is all real numbers. So my answers are now limited to either A or D. Okay, algebraically, we looked at what values I can substitute in for x, and the equation still works. Let me give you one that doesn't. How about y equals the square root of x? Let's start with a new equation. What if, okay, what if that was my equation? Okay, so you may not wonder, where did I get that equation? I just made it up just to give you another example to talk about this thing called domain. The domain I gave you, or the domain you were given in question 7, was all real numbers. So what does something look like that's not all real numbers? That's the purpose of my example up here. So y equals x squared. Can I plug in anything for x, just like I can for y equals x squared? No. What if I put a negative 16 in here? What is the square root of a negative 16? Is that possible? With what we know right now, this thing called real numbers, that's not possible. You might think, what about a negative 4? Negative 4, because square root says what two numbers can multiply by themselves to give me this negative 16. It's kind of the opposite. It's technically the inverse of this x squared concept. This x squared says take that number and multiply it by itself to give me something. The square root says I have this something and what two numbers multiplied together to give me that something. So a negative 4 times a negative 4 is a positive 16, because a negative times a negative is positive. Well, then what about a positive 4? A positive times a positive 4 is also 16. The only way to get a negative 16 is if I do a negative 4 times a positive 4, and that is no longer the definition of square. Square root says what two numbers can multiply by itself. So the two numbers have to be the same. There is no way of getting a negative 16 without the introduction of something we're going to talk about later in this course called imaginary numbers, but that's not what we know yet. So right now, the domain is not all real numbers. The domain of this one is x has to be greater than or equal to 0. I can square root any positive number. It may come out to be a weird decimal, but I can square root any positive number. I can also square root 0 because 0 times 0 is 0. Okay, so algebraically, that's what it looks like. I'm going to skip domain for, or range for a second. I'm going to keep with this idea of domain. Let's go to a graph. I'm going to graph y equals x squared minus 1. Y equals x squared minus 1. You just had to graph a bunch of these up here. So I'm going to assume, I don't have questions 1, 2, and 3 copied, but there were more graphs. Okay, I'm going to assume you know how to graph, but I'll talk through it a little bit. But the question for today, or the topic for today, is domain and range, not necessarily graphing. So if you remember from questions 1, 2, 3, and 4, the way I graph this is a parabola. It's a y equals x squared graph, so I know it's going to look something like this. Okay, that was just a rough sketch. But it's going to be shifted down 1. This guy right here says my graph is shifted down 1. Now, a normal y equals x squared, my parent function, looks like this. So this domain, this negative 1 shifts my graph down 1. So it was right here. The vertex was right here. Now it's right here. This does not have any kind of number in front of it, so it's my basic parent function of when x is 1, 1 squared is 1. So in both directions, when x is a negative 1, negative 1 squared is also 1. So when I move left or right 1 from this point here, I go up 1. When x is 2, or if I moved 2 units over from the vertex, I square that. Why would I square it? Because it tells me to. Y equals x squared. So when I move over 2 in the x direction, 2 squared is 4, and so I go up here to 4. And I sketch my parabola through those points that I just picked. And I can pick a whole bunch more to keep finding points to help me recognize my shape. Okay, what is the domain of this thing? Here's a key part. These arrows say that this pattern continues forever. Meaning this arrow, I know it looks like it's going up, but there's a slant to this line, so it's actually going to the left also. Meaning at some point in time, I will reach an x value that's way over here. It's going to be way up off my graph, not off my graph, off my computer screen. It'll still be on the graph, but it'll be off the computer screen, but it will eventually get there. Same over here. This arrow says that goes both up and to the right forever. So at some point in time, I will reach every single x value over here. The fact that it's a solid, continuous line tells me I will also hit every single x value along this x-axis. There will be a y value that corresponds to every x value. That was a very key point for the next question. There is an x value that corresponds to, there is a y value that corresponds to every x value along the x-axis. My domain from the graph is all real numbers, which is what we said from the equation. Okay, what does 1 look like that's not all real numbers? Let me do the y equals x squared that we did up above. Square root. It's early in the morning. I'm having a hard time talking. So let's look at y equals x squared. This is my graph of y equals x squared, just sketched. Okay, so let me just plug a few points in so you can see what I did. When x is 0, the square root of 0 is 0, because 0 times 0 is 0. When x is 1, the square root of 1 is 1, because 1 times 1 is 1. When x is 4, the square root of 4 is 2, because 2 times 2 is 4. So when x is 4, y is 2, and so on. When x is 9, y is 3. When x is 16, y is 4, and it is a sideways parabola. Something's weird happened. There's no bottom. Okay, there's nothing down here. There's no way I'm going to get a negative number out of here. And there's nothing over here. What is my domain? What x values does this graph pass through? Meaning, what x values have a y value associated with it? Remember I said up here, every x has a y value that is associated with it. There are no x or y values over here. X will never be a negative number because I'll never get a y value that goes with it. Over here I do. When x is 1, y is 1. When x is 2, y is whatever the square root of 2 is, 1.4, etc. When x is 3, and so on. When x is 1.1, 1.2. This is my domain. And what would that be? X is greater than 0, just like we said before up on the algebraic part. Okay, hope that helps. That's domain. I'm going to stick with domain for just a second longer. Let's cruise up here to question 5. Now, I chose my words carefully when I describe the domain here. Since this graph is continuous, meaning it's solid, I don't lift my pencil, there's no gaps in my graph. It's every single x value along the x-axis. Not true on question 5. Give the domain and range for this relation, meaning just some set of numbers, no special pattern, nothing special about, just a relation. Give my domain for this relation. The domain is the x values. This says when x is 2, y is 5. Another point, when x is 3, y is 7. There is no x value in between 2 and 3. If I were to graph this, I have a point at 2 and 3. Oh, sorry, 2 and 5. I have a point at 3 and 7. I have a point at 1 and 4. There's nothing in between here. It's not a solid line. So my domain is simply 2, 3, 1, and 0. The x values. Not 2.1, not 2.4. So I can't say my domain goes from, what's the smallest, 0? I can't say my domain goes from 0 to 4. It doesn't. It doesn't cover every single value between 0 and 4. The domain is only these individual specific x values. Okay? If my graph or my equation has a continuous, let me get rid of this guy, has a continuous function, meaning it connects the dots between the points, then it is something like this, where x is everything between 0 and infinity. But if it's just a set of points that are listed, then you have to list the domain as just a set of points. Okay. You may ask, well, how do I know if it's continuous? If it's in an equation format, it will be continuous until, sorry, I hate the untils, kind of sounds like English. It will be continuous unless we get to something down the road called rational functions. And there's a few functions we have to worry about. For right now, everything that we know is continuous. Okay? All right. It might be a limited continuous function, like this one down here. This is continuous, but it's restricted to just everything greater than or equal to 0. But in that domain, it is continuous. There's no hole in the middle of this. We will get to this thing called holes and gaps and things, but forget that right now. That's later. Okay, so that's domain. Domain is x. Well, then you could probably guess then the range must be y, because there's two variables, x and y. So domain represents all the possible x values that you can plug into an equation. Well, when you plug a number into an equation, something happens. You work it all out, and you get a number coming out of the equation. This whole idea of a function. When you plug something in, something comes out. Domain is what you plug in, range is what comes out. X is what you plug in, typically, if it's just y and x, and your range is what comes out, or your y value. So, if I look at this function, or this equation, y equals x squared minus 1, this one's much easier to see graphically, but we'll keep going with it algebraically. What's the smallest x value I can plug in? Well, you'd say like a negative infinity. Okay, let's plug in a very, very large negative number. What happens to it? When you square it, it becomes positive, like a negative 10. When I square a negative 10, it becomes a positive 100. It becomes way up here. When I subtract 1 from it, it's still way up here. If I put in a negative 1,000, you get a million minus 1. And again, it's way up here. So let's think about, what if I plugged in 0? When I plug in 0, 0 squared is 0, minus 1 is a negative 1. Negative 1 is right here on my graph. When x is 0, y is a negative 1. So that's technically the smallest I can plug in. If I start plugging in positive numbers now, my graph turns and goes right back up. Range is much easier to see graphically, so I'm just going to continue with showing it to you on the graph. When I plug in very large negative numbers, I get big positive numbers because of the squaring properties. My graph comes down as I plug in numbers closer to 0, and at 0, my graph kind of hits the bottom. Remember, we're talking y values, not x values anymore. So my y values start way up here. As I plug in numbers for x that are closer to 0, my y values get smaller until I reach this negative 1. Then when I plug in values for x that are positive, my y values start getting larger again, and they just keep on going forever. So what's my range? My range is the set of all y values. So what y values am I passing through? Sorry, didn't mean to do that. Everything greater than or equal to a negative 1. There are no parts of my graph down here at negative 2, negative 3. My graph doesn't reach those values. In this equation, my graph will never pass through a negative 1. Or another way of saying it, no matter what I plug in for x, my y value, the output, will never be a negative 2. It'll never be a negative 3, and so on. My range is y is greater than a negative, or equal to, a negative 1. So answer to question 7 is D. What about this guy? I know this one's not on the test or the homework, but it's a good one to look at. Look at your graph. Will y ever be a negative number? Nope. My graph starts at 0 on the y-axis, and it goes up. So my y values for this equation would be y is greater than or equal to 0. There's my range. My domain is x is greater than or equal to 0. That is my domain. If we were to take this graph, this one right here, and shift it over, and let's just say over 2 and up 1, my domain is x is greater than or equal to 2. The smallest x value is 2. There's nothing over here. My range is y is greater than or equal to 1. There's nothing down here. The smallest y value, right? Y-axis, x-axis. The smallest y value is a positive 1. There's nothing down here. That equation, just in case you're wondering, would look like this. The square root of x minus 2 plus 1. Okay, I hope that helped for domain and range. If not, let me know and I'll try again. All right. So, does this equation represent a function? Question 8 was also asked. So what is this? Remember up here I said relation? What is the difference between a relation and a function? A relation has no special relationship. It's just a set of points. Okay, there doesn't have to be a pattern. There doesn't have to be any special properties. It's just a set of points. Okay, so this one up here says state whether this is a function, and question number 8 says state whether this is a function. Let's do question 8 first. Is this a function? Well, I like looking at the graph because graphically it's easier to see. So remember, this is an absolute value function. It's going to look like a V. So it's an absolute value function that has been shifted right 2 and up 1. When x is 2, y is 1, and I simply get my v coming up, coming up off of that. Its slope is 1 to 1 on both sides. If I move over 1 in the x direction, I go up 1 in the y direction. If I go over 2, I go up 2, and so on. Notice that is different than the quadratic function. The quadratic function, when I went over 1, I went up 1. But when I went over 2, I went up 4. There's a different slope to this one compared to this one over here. Okay, I'm going to have to, just for this recording, assume that we can graph an absolute value. But if we need more help, I can do that also. So, back to the question. Does this equation represent a function? A function says, for every x, there's just one y value associated with it. So remember over here I talked about every x value here, when I go to the graph, there is a y value that goes with it. When x is a negative 2, if I cruise up here and look at the point that was plotted, there's just one y value that goes with it. When x is a negative 1.5, there's just one y value, and so on. Same here. When x is 2, there's just one y value. When x is 3, there's just one y value, and so on. Definition of a function. For every x, there's just one y value that goes with it. Okay, what kind of graph would not be a function? How about a circle? If you were to graph a circle, or something kind of like a circle, when I look at this x value right here, there are two different y values that go with the x value of a negative, whatever that is, negative 1, negative half. When x is a positive 1 or so, there are two different y values that go with it. This is an equation, something like x squared plus y squared equals 1 or 2 or 5 or whatever. Excuse me. So this is an equation. It is a graph. It's just not a function. And simply the definition of a function says if you draw a vertical line through your graph, it can only pass through once. If it passes through twice, it's not a function. And you may ask, well, who cares? Well, mathematically, when you make something called a prediction based upon your past data, it's pretty important for it to be a function. But that's another topic for another time. So this idea of a function is simply based upon a definition. Okay. So does this represent a function? Yes. So what does that look like in a data set? Is this a function? Yes. When x is 2, y is 5. Is there any more places where x is 2? Nope. Had we added one more data point when x is 2, y is 7? No longer a function. Now when x is 2, y is 5, or when x is 2, y could be 7. There are two y values, 5 and 7, that are associated with the number 2, or the x value of 2. Okay, since there's not this 0.27, the 2 is okay. It only goes to one y value. When x is 3, y is 7. When x is 1, y is 4. These x values don't have another ordered pair that says when x is 3, y is 2, or something other than one y value. So yes, this is a function. Okay, recording's getting kind of long. I think I'm gonna call that good. And if you still have questions, shoot me an email and I'll go at it again.